Hello and welcome, dear all enthusiastic learners. I am absolutely delighted to see each and every one of you here today. My name is Dr. Amar Kumar De and I will be your tutor for week 3, module 2, lecture titled Characteristic of Biopotential Electrodes for the SWAYAM course on Biomedical Instrumentation and Sensors. Thank you once again for joining us. Your willingness to learn and grow is truly commendable. I hope you have been enjoying the learning journey so far. Today, we are going to dive deeper into the topic biopotential electrodes. Before we dive into the today's topic, let me take a moment to recap what we covered in our previous modules. In our last module, we explored bioelectric potentials, examples of bioelectric potentials, insights and applications of bioelectric potentials, origin of bioelectric potentials, resting potentials, depolarization, repolarization, bioelectrodes. We explored the history of bioelectric potentials and found that there is a remarkable progress from early discoveries in animal electricity to sophisticated techniques for measuring and analyzing electrical signals in living organisms. We defined what biopotential is, since the understanding of bioelectric potentials continues to evolve, opening up new avenues for biomedical engineering, neuroscience, and healthcare applications. In examples of biopotential, we come to know about biopotential signals like electrocardiograph, electroencephalograph, and electromyograph. Then we look into the insights and advancement of biopotentials in biomedical engineering and found that bioelectric potentials are crucial electrical signals that reflects the complex physiological processes within the human body. Their measurement and analysis are fundamental to biomedical engineering, enabling medical diagnostics, research advancement, and development of innovative technologies to improve human health and well-being. We discuss the origin of bioelectric potentials and learned the concepts of resting potentials, depolarization, and repolarizations. Finally, we defined bioelectrode and discusses the various way to categorize the bioelectrodes. Now, before we embark onto today's learning journey together, let's me take a moment to give you an overview of what we are going to expect from today's module. Today, we will explore various aspects related to biopotential, bioelectrodes, essential topics in the field of biomedical engineering. We start with the topic characteristic of biopotential, then we will explore bioelectrode characteristic. Simultaneously, we will discuss the Nernst equation. In Nernst equation, we will calculate the electrode potential and understand the relationship between ion concentration and electrode potential with an example. We will also focus on the concepts of half cell potentials and polarization. Thus, with the knowledge of above all, we are going to implement the equivalent circuit for biopotential electrode. Now, let's proceed to explore each topics in detail. Now, let's get started with the characteristic of biopotential. As we already discussed in our previous module that biopotential are electrical signals generated by living organisms such as humans and animals. These electrical signals are essential for various physiological processes and can be measured using biopotential electrodes. Let's explore the key characteristics of biopotentials. The first characteristic is its electrical nature. Biopotentials are electrical in nature, means they involve the flow of charged particles such as ions through biological tissues. This charged particle creates electrical potentials or voltage differences which can be detected and measured. The next characteristic is origin. Biopotential originated from the excitable tissues of body, primarily nerve cells, neuron and muscle cells. Neuron produce action potential while muscle cells produce electrical signals during muscle contractions. Then in the next biopotential characteristic we have measurement sites. Biopotential can be measured at various sites on the body depending on the specific physiological process being studied. Common measurement sites includes scalp for electroencephalography, the skin surface for electrocardiography, and inside the body for intracortical recordings. Next characteristic is the amplitude. The amplitude of biopotential varies depending on the specific source and measurement size. EEG signals, for example, have small amplitudes in microvolt range, while ECG signals have large amplitude in millivolt range. Now, the next one is frequency content. Biopotential exhibit varying frequency content that reflects the understanding physiological activities. EEG signals, for instance, have frequency component in the range of 0.5 to 100 Hz, while ECG signals have dominant frequencies related to heart rate and cardiac activities. The next characteristic we have the waveform shape. Biopotential waveform have characteristic shape that represent specific physiological event they originated from. For instance, ECG waveform consists of P wave, QRS complex and T waves, which corresponds to different stages of cardiac cycles. Then the next characteristic is noise sensitivity. Biopotentials are susceptible to noise, which can interfere with the actual measurement and interpretations of the signal. Careful signal processing and noise reduction techniques are crucial to obtain high quality biopotential recording. Finally, in signal propagation, which is the important characteristic, biopotential propagates through the body tissues and fluids, enabling them to detect at remote measurement sites. For instance, action potential generated in the nerve cell can travel along the axon to be measured at the surface of the skin through electromyography. Understanding the characteristics of biopotential is crucial for accurate measurement and interpreting the electrical signals, thereby unlocking valuable insights into the functioning of human body. Bioelectrode possesses several important characteristics that make them suitable for interfacing with living organism and recording their electrical signals. Here are some key characteristics of bioelectrodes. The first and the most important characteristic is the biocompatibility. Bioelectrodes are designed to be biocompatible, meaning they do not cause harm or adverse reaction when in contact with living tissues. They are made from materials that are safe for use within the body or on the skin. The second characteristic is sensitivity. Bioelectrode must be sensitive enough to detect weak electrical signals produced by biological process. They should be able to pick up subtle changes in electrical activities of tissues and organ. The third characteristic is selectivity. In certain application, it is essential for bioelectrode to be selective in detecting specific types of electrical signals. For example, in EEG recording, the electrode should mainly capture brain wave signals and minimize interferences from other sources. Stability is an important characteristic. Bioelectrode need to maintain their electrical properties over the time to ensure accurate and consistent signal recording. They should not drift or degrade significantly during use. Low noise characteristic of bioelectrode. To obtain clear and reliable signals, bioelectrode should have low noise levels, reducing unwanted interferences and artifacts that could obstruct the biological signal. The next characteristic is longevity. Some applications such as long-term monitoring or implantations, bioelectrode should have a reasonable lifespan, providing real signal recording over extended periods without needing frequent replacements. The next characteristic is easy of use. Obviously, bioelectrode should be designed for easy placement and removal from the body's surface within the bodies during surgical procedures. They should be user friendly and not causes discomfort to patients or subject. The next characteristic is sterility. In clinical settings or applications involve implantable bioelectrodes. Maintaining sterility is crucial to prevent infection or complications. The next characteristic is high signal to noise ratio. A high signal to noise ratio ensures that recorded electrical signals are stored in clear relative to any background noise, making data analysis more accurate. Next characteristic is miniaturization. In some applications, particularly in implantable bioelectrodes, miniaturization is essential to reduce device size and invasiveness. Finally, the last characteristic is flexibility. Flexible bioelectrodes are advantageous, especially when conforming to irregular body surfaces or when using in wearable devices. So, this characteristic plays a crucial role in the successful applications of bioelectrode in various fields, including medical diagnostics, research and clinical treatment. Engineers and researchers continuously working to improve bioelectrode technologies to enhance signal quality, patient comfort and overall performances. Now, there are some other important characteristics of bioelectrodes such as the electrode electrolyte interface, polarization, which affects the selection of bioelectrode for particular applications. But before we get into them, we need to understand few basic concepts like Nernst equation and half cell potential. So let us start with the Nernst equation. Now that we covered some of the key characteristics of the biopotential and bioelectrode, let's explore fundamental concept of electrochemistry that has a significant implication on ion concentration and electrode potential, the Nernst equation. Now let's talk about the Nernst equation. First of all, what is Nernst equation is, well, in physiology, puts simple, the Nernst equation can be used to calculate an ion equilibrium potential, that is the voltage that is necessary to offset the movement of ion down an ion concentration gradient. For this particular situation, let us imagine we have ion concentration gradient such that we have a higher concentration of ions inside the cell and a lower concentration of ions outside the cell. It worth nothing that for each compartment we have equal concentration of cations and anions. This is in accordance with the law of electrical neutrality, which means that the amount of positive charge must equal to the amount of negative charge. Another way of thinking, or it is a little simplified. You could have imagined you have an equal concentration of cations and anions for each compartment. Now, for the purpose of Nernst equation, let's simplify it little bit. We just focus on the cations, ignoring the presence of the anions. So the Nernst equation arises from the behavior of ion in the solution, specifically on what determine the net movement of the ion in an aqueous solution is really two things. First of all, the ion move down the concentration gradient, that is, they tend to move from region of high concentration towards the region of low concentration. This can be symbolized here as a vector. Direction of this vector indicates the direction of the net ionic movement from high to low concentration, and then the size of the vector indicates the magnitude or the strength of the tendency that the movement to occur. The greater the concentration gradient, the greater will be the strength of the tendency of the ion to move down the concentration gradient. The situation where the concentration gradient is reduced, we can still expect ion to move from the region of high concentration region to low concentration region, but the strength of the tendency is also reduced, which ultimately means that the rate of ion movement also be reduced. You can imagine a situation where if you do allow concentration gradient to disappear, this is now the concentration inside and outside, they are equal, then now we have no net movements of ion from the ion would be at equilibrium. The other factors that determine how ion moves into a solution, here is the presence of electrical field or the electrical gradient. Ions tend to move down their electrical gradient. In this situation, we just assume that we have equal concentration both inside and outside of our cell, so that we can ignore the effect of concentration gradient. But now a battery such that the negative terminal is oriented towards the inside and the positive terminal is towards the outside of the cell. This creates an electrical field which goes to cause the ion tend to move inside the cell. In this situation, this is because the ions are going to be attracted towards the negative terminal on the inside of the cell and equally repel from the positive terminal which is placed outside of our cell. Again, the strength of this tendency of the ion to move down the electrical gradient can be presented as a vector, in this case pointing towards where once again the magnitude of the vector represents the strength of the tendency for the ion to move down the electrical gradient. We can imagine that if the battery having much smaller voltage creating a weaker electric field, then the strength of the tendency of the ion to move down the electric gradient will equally be reduced. So what about the situation here? Let imagine the situation that combines our first two conditions, where first of all we have an ion concentration gradient, that is greater concentration of cation inside the cell to the outside of the cell, but then we also have this battery connected that creates an electrical field such that the negative terminal is oriented inside the cell and the positive terminal is outside the cell. On one hand, we have concentration gradient which tends to favor outward movement, but on the other hand we have the electrical gradient which would favor the movement. So that the question is, in which way is the ion going to move? If we think about it, just because we are comparing an ionic concentration gradient with electrical gradient, you seem like two very different things how to answer this particular question. That is how we can compare the size of concentration gradient to size of electrical gradient. So that's where the Nernst equation comes into picture. First of all, here is the Nernst equation. It is a mathematical equation used to describe the relationship between the ion concentration and electrode potential in electrochemical system. It helps us to understand the change in ionic concentration affects the electrical potential of electrode. It's already derived and is given by the equation highlighted in this equation. The equilibrium potential denoted by capital E is equal to RT over NF times natural log concentration of the ion outside over the concentration of ion inside. In this equation, R is the gas constant, T is the temperature in Kelvin, N, small n, is the number of electrons involved in the chemical reaction, F is Faraday constant. In representing the natural logarithm function, F is Faraday's constant, C1 and C2 are concentration of ion, F1 and F2 are the respective active coefficients of the ion on two sides of the membrane, X out and X in are the respective concentration outside and inside of the cell. On substituting the values of the constant, R the gas constant, T the temperature constant, N the number of electrons involved in the chemical reaction, F Faraday constant, also converting natural log to log base 10 and converting volt to millivolt, we get the equation as E is equal to 61.5 times log base 10 X out upon X in millivolt. Now let's come back to the question again, in which way the ions move. To address this, let's assume some concentration inside and outside compartment. Let's assume the inside concentration is 100 millimolar and outside concentration is 6 millimolar. So we can substitute the values into simplified Nernst equation, which can be given us the following potential. On solving and substituting the values, we get the electrical potential as minus of 75.03. We approximately considered it to be a minus of 75 millivolts. Now, the electrical potential is minus of 75 millivolt. What does it means? It means that giving this particular concentration gradient, the battery would have to be precisely 75 millivolt to perfectly offset the movement of the ion down it, concentration gradient. Now, if we assume that the battery is less than minus 75 millivolt, say it is some minus 50 millivolt battery, such that we have negative 50 millivolt inside the compartment as compared to the outside, then the size of our voltage gradient will actually weaker than our concentration gradient. Now, we can expect the ion to travel down the concentration, that is the concentration gradient win in this particular case. Now, suppose the voltage is negative 90 millivolt, such that we have a negative 90 millivolt inside the cell. In this case, the voltage is strong than the equilibrium potential of the ion. So, battery will win. So, the ion will now travel from the region of low concentration to a region of high concentration. So that this is how the Nernst equation is applied in this particular case. In simpler term, the Nernst equation help us to calculate the concentration of ion, their electrical charges affect the electrical potential across the cell membrane. It tells us how much voltage is generated, where ion move from one side of the membrane to other. The Nernst equation in particular importance in understanding how nerve cell neuron transmit electrical signals through their membrane. The movement of ions like sodium, potassium, calcium across the cell membrane is crucial for generating action potential, which are the electrical impulses that enable communication between different parts of the nerve system. With this, we come to an end of today's session. In the next session, we will be covering electrodes and its type. Till then, have a nice day. Thank you.